All right, so picking up where we left off last time, we were talking about flux through a curve. And remember, flux through a curve is basically the same idea as flux through a surface. If a vector field represents the velocity, or density times the velocity, if a vector field in some way represents a fluid flow, then this expression called flux represents, appropriate to how the vector field represents the fluid, represents the flow rate. It represents how much total quantity, again in whatever appropriate sense, quantity per unit time of fluid flowing through the thing. Now, of course, here, this being a two-dimensional situation, it's a line segment, not a rectangle, right? Not a flat thing in, well, let's see how to say it. Not a flat two-dimensional thing in 3 space. Now it's a flat one-dimensional thing in 2 space. Okay. All right. And so the again, the size, now length instead of area. Okay. So a reasonable question then. Suppose you have a region, a two-dimensional region like this, and you want to talk about the flux through the boundary. So there's the curve that is the boundary, right? And we want to talk about how would I, add up over all the little pieces of the boundary. How would I, add up all of that flux? Okay. So the first thing I'm going to do is suggest that we not pay attention to this yet, or this. Let's ignore that for the moment. Right? We've got a vector field like this, and for our looking at our curve, again, here's our boundary curve. Looking at a little piece of the boundary curve, some little piece like that of size ds. Oops, let's do this. Little piece of size ds, and given a normal vector for that little piece of surface, what we have here on each little piece of the boundary curve, we know the vector field, we know the normal vector, unit normal vector that is, and so we can just write down exactly how much flux there is. The amount of flux through that little piece, which you might call d phi, is just exactly borrowing from the formula on the previous page, f dot n times the length of that little piece. Okay, so that leaves us, now again, we're going to make an argument that the whole is the sum of the parts, right? And so this, of course, this little differential flux that we just computed is just on that one little piece. When you add up over the whole curve, that's an integral. And here's the bad news. This is an integral that we don't really recognize, right? Looking at this expression right there, we've never seen something quite like that before. We've seen integrals with a ds at the end, right? But those were scalar line integrals. There's something kind of intrinsically not scalar about this, in the sense that really what we're interested in is a vector field. So it's not really quite that. We have seen integral f dot t ds. But that's not what we have here. Here we have f dot n ds. So something is different. We don't really know how to compute this. Right? Now you can brute force it. You can write down for your curve an explicit formula for your unit normal vector, right? And then compute this as a scalar line integral. And I suppose if you want to brute force, that's an option, but it's a pretty bad option. Okay. All right. So here's the move. Here's the clever move, and this is where I'm going to bring back all of this stuff. Note that the dot product that we're looking at here, let's see here, I'll use like this. We've got f dot n. You can see those vectors. Here they are, f and n. Right? Notice that if I take these vectors and do a 90-degree rotation of each one, what happens when I take the normal vector and rotate 90 degrees counterclockwise? I get the tangent vector. I get our usual unit tangent vector for that piece of curve. And what happens if I do a 90-degree rotation of some vector field p comma q? Well, now this isn't going to be something we particularly recognize. But we do know how to do a 90-degree rotation. This is a linear algebra thing, right? Again, make sure that you're good with that kind of linear algebra. And p comma q turns into negative q comma p. So why do we care that this is a 90-degree rotation? What's nice about this being a 90-degree rotation is that this dot product that we're interested in is therefore equal to this dot product. Not the original vector field dot n, but the rotated vector field that I call f perp, little perpendicular subscript, dot t. And why are those dot products the same? Well, because dot products only depend on magnitude and angle. And rotating preserves the magnitudes of these two vectors, and it preserves the angle between these two vectors. So it's kind of a slick little move. So because I have made this observation, I can replace this blue dot product, f dot n, with this green dot product, f perp dot t. Who cares? Why is this a win? This is a win because look at what kind of an integral we've got now. We have a regular old, plain old vector line integral that we have lots of experience with computing, right? Because we no longer have nds, now we have tds, and tds is exactly what dx is. So we've turned a problem we don't know how to solve into a problem that we have several tools for solving. Okay. All right. Now, having made that observation, so we've got a bunch of options, a bunch of things we can do. And I'm sorry. Yeah.
Sorry, could you just explain one more time why TDS is DX?
So that goes back to chapter 3.
Okay.
Yeah.
Okay.
It's a bunch of stuff in there. Yeah, right. Yeah. Okay. So we've got this integral right here. Oh, why am I in that color mode? This integral right here, it is a regular vector line integral. Even better, it's a vector line integral over a boundary. Again, keep in mind, we're trying to compute the flux through a boundary of a two-dimensional region. So this is a boundary vector line integral. It's a circulation. And we have this awesome theorem that tells us how to compute circulations, Green's theorem. Right? If you have a boundary circulation, you can rewrite that as a double integral over the interior of Green's operator. Now this step right here is that's doing all the heavy lifting. This is the big move in this calculation. Now a couple of details that we have to work out in order to proceed here. How are we going to compute Green's operator here? We recall that Green's operator is an x partial of one of the components minus a y partial of one of the other components. Now, students very often went a little too fast and loose with understanding of that formula. We memorize it as dq dx minus dp dy, but remember, that's if you're taking Green's operator of p comma q. We aren't. We're taking Green's operator of f perp. It is not p comma q, right? So better to think about Green's operator as the x partial of the second coordinate. Now, our second coordinate is p. Minus the y partial of the first coordinate. The first coordinate is minus q. Right, so this is what happens when you apply Green's operator to this rotated f perp minus q comma p vector field. Let me get that. And at this point, it's kind of all over but the shouting. These minus signs cancel, right? And all we have is dp dx plus dq dy, which you may recall, again, flashback to chapter 3, this is the formula for what we called divergence, for which we have this notation. And we have some geometric interpretations. So, There's our new theorem. We started with Green's theorem in some sense. Let me say that differently. Green's theorem was kind of underneath all of this. Green's theorem did the big step, but having done that, we now have a new theorem that we call the 2D divergence theorem. And notice, just like Green's theorem, it relates an integral computed on the boundary, named boundary flux, to an integral computed over the interior, namely a double integral of divergence. Okay. So that's how that little connection works. It's a real slick move. Let's see an example of this. We are being asked to compute a flux. Notice it's written very naturally in this form that we don't like, right? This form that at a glance we don't know how to compute it. But then we make a quick observation, which is that the curve over which I'm supposed to compute this flux, the unit circle oriented outward, that is exactly a boundary. Right? Pretty good. And being as it is a boundary, we can apply our new theorem. We can apply our 2D divergence theorem, and we're not even going to particularly touch the things that are inside of what we've been asked to compute. We're just going to say, oh, that thing, oh yeah, that's flux, and we're going to use this awesome theorem to compute it instead. Forget about the n. Forget about the ds. We've been asked to compute a boundary flux, and boundary flux is double integral of divergence. Everybody good? Yeah.
Do you need to know like the direction of the boundary, or it doesn't matter?
Yeah, yes, you do, but again, that's all according to convention. And so when you talk about bad color, sorry. If you have a three-dimensional, if you have a region, a two-dimensional region, right, and you want to talk about the boundary of that two-dimensional region, that boundary is oriented according to certain conventions, right? And the convention is always when you have a boundary, it's oriented counterclockwise, you might say, or as is really more convenient in this case, it's oriented in the direction that has the region on your left as you go that way. Is that cool?
So for this question, we can assume that it's like on the left. We don't need to.
Well, we don't have to assume it. We've already made this observation here that outward, that being the convention for orthogonal orientations, when you rotate that 90 degrees counterclockwise, that puts you going the direction such that the region is then on your left. So it just works, right? So that's conveniently already been done for us. Does that make sense? Okay. All righty. So this integral is mostly done at this point. A couple little details that have to be pounded out. We do have to compute the divergence. Again, we've got this vector field F. Divergence is a formula, right? So we're going to take the, let's see here, the x partial of the first component, which is just 2. And then we're going to add the y partial of the second component, conveniently, just minus 5. And so, well, wonderful bit of good fortune, the divergence ends up just being minus 3. And then again, easy interval. How we doing? Okay. Oh, I'm sorry. I didn't see that. Yeah.
Is the way you would interpret this is you'd say like there's a flux of 3 pi into the boundary?
Out of. Yeah. So again, when we say when we talk about boundary flux, and this is another sort of one of these arbitrary but standard conventions that we just have to stick with so that previous work will always work, right? Boundary flux means the orientation is outward.
But if it's
across
negative,
that boundary.
Does that mean it's inward? You know what I mean?
Yeah, that's right. When we say an orientation, what that means is that's the direction that we're going to consider the positive direction. And so if the value is negative, then it's the opposite of that, right? So yeah, that's right. So if your outward boundary flux is -6, well, that means that there's a flow inward into the thing. Yeah. Okay. All right. Now, here's a different point of view on this theorem. Again, we got this brand new theorem, very cool theorem, that boundary flux is computed with a double integral of divergence. By the way, we call this the 2D version because there is a 3D version that we're going to see soon-ish, I guess late next week, if I had to guess. Oh, speaking of next week, I am making progress on the grading of the midterm exam. I've graded 3 of the 5 pages. It's moving along pretty well, and I am going to make every effort to get the grading done this weekend. So fingers crossed. No promises, but that's the goal. Okay. And I'll of course email when it's all done. Okay. So yeah, here's a different take on that theorem. We got to the 2D divergence theorem by basically tweaking Green's theorem. But you can instead just view it as itself being just another accumulating quantity. And basically, whenever you have an accumulating quantity, you can rewrite the quantity as an integral, and an integral which on each little piece is density times size, and you get a new theorem. Right? So this is the reason that we're so interested in this idea of accumulation is because accumulation leads to theorems. Right? So let me walk you through how that works here. Why is boundary flux an accumulating quantity? Well, here is a whole set, the boundary of which is like this. So there's the boundary of the whole. Now let's look at the left piece. Here's what its boundary looks like. Right, that's the boundary of the of D1. Oh, come on, eraser. D1. And then here's the right piece, D2. What does its boundary look like? Well, its boundary looks like this. And we can find ourselves asking, well, does green plus blue equal to purple? Well, it's looking good over here. It's looking good over here. Concerned about this stuff in the middle. Right? This stuff in the middle is what you might call my problem. This that I leave unerased, this is the impediment. This is the problem. This is the shortcoming. This is why they wouldn't be equal if they weren't equal. But here's the thing. What we have here is a single curve. This single curve right here, and we're computing fluxes through that single curve twice with opposite orientations, and they cancel. Shockingly similar to the argument that we made for Green's theorem. And the big difference being that, again, it's still on a single curve. This time we're computing flux, not vector line integral. The orientations are opposite in the sense that they point oppositely across the curve as opposed to oppositely along the curve. Right? So it's geometrically different, of course. But it's really analogous. Right? It's morally kind of equivalent. Certainly very, very, very similar. Okay. All right. So you can ignore Green's theorem and come up with the theorem, with our two-dimensional divergence theorem, just by pointing out, well, this is an accumulating quantity, and following the usual pattern. Okay. A real quick summary before we go on to the next thing. These are 3 kinds of accumulation and density arguments that we've made. Of course, we spent much of Chapter 5, roughly speaking, talking about stuff like this. I'm using mass just because it's, I think, the most relatable and sort of convenient metaphor for these kinds of arguments. But we've done, of course, done many things other than mass. But the whole is the sum of the parts. That's how mass works, right? If you have a cake and you cut it into pieces, you still have the same amount of cake. Right? Whole is the sum of the parts, and then for any given little piece, there is an associated density. That being, I mean, again, we're broadening our sense of what density is to be accumulating quantity per unit size. Whatever the accumulating quantity, whatever the appropriate notion of size. And so we have this idea of density here, which of course we call mass density. And why do we call this mass density? Well, we call it mass density because the corresponding accumulating quantity is mass. It's the density that comes up when you're talking about mass, so thus the name mass density. All right. So here are the two theorems that we've done over the last couple of days, and again, very tersely, very compactly, hitting the highlights only, written down. But look how extremely similar these theorems are. Even though this is about something physical, literally physical, and these aren't. These are about, mathematical expressions that we might be able to relate to things that are physical, but they're not really physical. They're kind of mathematical creations, right? Nevertheless, they behave just like stuff. They're accumulating quantity, so the whole is the sum of the parts. For each one of them, you can talk about the associated notion of density. That being the integrand that comes up, right, as you go through the argument. And again, we label these densities in what I'll call the obvious way. Why do we call this one circulation density? Well, because circulation is the quantity in question that we're talking about. And why do we call this one flux density? Well, again, because flux was the accumulating quantity we were talking about. Everybody happy? All right, so just so you know, these terms here are not equally common. Mass density is pretty uniformly standard, right? Everybody knows that term. This term here, flux density, extremely common. So I'll point out that in my days, doing physics classes way back when, my physics professors said the term flux density at least as much, I think more, than they said the word divergence. Now, of course, that's what it is. It is divergence, right? Mathematicians tend to say divergence. My experience was, and again, long ago, different school, right? But still, very common in the physics community, flux density, which I think is fantastic. I actually kind of prefer the term flux density. It's very communicative. It's talking about literally what are you doing? What is the object you're talking about, and what aspect of it are you interested in describing? I think it's about as direct and communicative as you could get. So be prepared for that. The term circulation density is not as common. That said, it is still extremely communicative. It's very transparent terminology, right? The word Green's operator is pretty made up. The word curl or rote, right? Again, they're trying to conjure images, but circulation density is pretty literal and just hitting the nail right on the head. This term is around. Some people do use it. There are other terms that get used. Vorticity is another common term that they use for this. Again, that conjures nicely, right? But it's just not as right on nail on the head as this is. Okay. Next thing, let's talk about the fundamental theorem of calculus. I know y'all know fundamental theorem of calculus. I'm going to take a completely different point of view on it than you've probably seen, I would expect. I'm going to point out that the fundamental theorem of calculus, even though you didn't view it this way, presumably, in your Calc 1 classes, is actually another accumulation and density theorem. Structurally, strategically, it's just like Green's theorem. and it's just like the 2D divergence theorem. So now a little bit different, of course, everything's different, the context matters. We're going to be interested in this expression here that I'm going to call change. We're not interested in circulation as an accumulating quantity. We're not interested in boundary flux as an accumulating quantity. Here, change. You give me an interval. On that interval, a given function f will change by a certain amount. So I want us to view change, which I denote with the capital Greek letter delta, which I think is a pretty natural choice. I want to think of change as being, while it is, of course, on the one hand, a formula, right? So with circulation, I want to think of it as being a kind of a stuff. It is an accumulating quantity. Okay. Now, let me try to persuade you that this is an accumulating quantity. I think it's a pretty easy pitch. Here I have a picture of a function that's changing. You can see it change right there, right? And so here we go. We have an interval from A to B. This interval from A to B causes the function f to change from that value to that value. So it's said differently, there is a certain amount of change happening on this interval. Now, I'm going to cut this interval into two pieces. Let's see here. I'm going to do it about like this. On that green subinterval, the function changes, looks to be about like that. Okay. And now, okay, let's look at the remaining part of this subinterval. Over that blue part of the interval, the function changes about like that. And so, I mean, again, I think it's pretty clear how this is going to work. But, does purple equal to green plus blue? Well, yeah, of course it does. Okay. The amount that f changed from here to here plus the change from here to here, of course, it gives me the total change from my there all the way over to here. Everybody buy it? Okay. So, change is an accumulating quantity. The whole is the sum of the parts. On any little piece, let me try to get both of these onto the picture at the same time. On any given little piece, oh gosh, I'll use orange. How much does a function change over some little subinterval? And how does that relate to how much the input moved? Well, that's what the derivative is. Right? The derivative is literally, actually, let me erase these. I want to recover some of these colors. The derivative is literally telling me what I'm going to call the change density. Now, you can see this in a couple of different ways. For one thing, you just kind of notice the pattern, right? But I'll just draw a picture here that if I have, let's see here, I'll use green. If I have some little dx, right, and if there is a corresponding amount of change, right, the derivative is the relationship between those. The derivative f prime is let's see here. It's the this divided by that, if you like. Again, you can think of that as being rise over the run, which is the common Calc 1 point of view. I, of course, am going to be pushing the point of view that's going to link this up with what we've been doing. Don't think of the blue here as being rise. Think of it as change. Don't think of the green as being run. Think of it as size. So this isn't rise over the run. This is change per unit size. And again, thus, density. Is that cool? Weird point of view, isn't it? Right? I mean, you have a much more familiar point of view that derivatives are about slopes. right? And that's not wrong, I suppose, and it's fine, and it's useful in a lot of contexts. But in this context, the fact that the derivative can be thought of as that slope isn't really quite the point. The point is that in this context, the derivative can be thought of as a density associated to yet another accumulating quantity. Change. All right, now, so what? Who cares? Aside from the fact that I guess it's a little bit of an eyebrow raiser that our Green's theorem and our 2D divergence theorem are structurally just like the fundamental theorem of calculus, right? Different context, of course, but they really have a lot in common with the fundamental theorem of calculus. I think that's interesting right off the bat. But here's another reason I like this comparison. What else does the derivative do for us? Well, the derivative is something we can see. I can see, for example, there, the derivative is significant. Dare I say large. Whereas over here, seems pretty clear that the derivative is, I'm going to say 0, but anyways, definitely very small at most. So the derivative, we have tons of experience seeing it, and I can point right to it. There it is. That's a lot easier to recognize geometrically. So I make the modest observation that the derivative tells us how much change is happening where. Well, again, of course it does. The fact that the derivative is, let's say, call it 0 along in here, of course that means the function is not changing much here, if any. Right? Whereas the fact that the derivative is larger here tells us that, yeah, along in here is where the function is changing by a significant amount. So, neat fact then, whatever your density is, whatever your integrand is in your theorem, and any of these accumulation theorems, the density is literally telling you how much your quantity is happening wherever it is that you might happen to be looking. Okay, so now, right off the bat, I have a favorite application of this, and that is, let me just kind of walk through, set it a little bit differently again. We've got a certain amount of change that happens over the course of the interval. How do I compute that change? Well, it's f of b minus f of a, which is computed by looking at the value at b and the value at a. And so the boundary, the points A and B, is where we're measuring this change. Of course it is, f of b minus f of a. It says it right there in the formula, right? But hopefully no one's weirded out by me suggesting that even though the change is measured at the endpoints, the change is not actually happening at the endpoints. No, of course, it's perfectly obvious. Look at the graph, for crying out loud. Here's where the function's changing. You can see it in the picture. So now I made an observation that I presented as being creepy and counterintuitive, and I think that's fair. Some time ago, let's see, what was this? Probably that may have been Wednesday. I'm not sure. But even though, I said dramatically, even though circulation is measured on the boundary, you should think of it as actually happening in the interior, and it seems really weird and counterintuitive and unrelatable. And surely you jest, right? But notice, that's the exact same thing that we just got through accepting as being basically obvious in the other context, right? So the idea that something that's computed on the boundary would be viewed as actually happening in the interior, not that weird, right? So again, creepy idea in the context of Green's theorem, certainly the first time you see it. Pretty relatable, in fact. Okay. Now we can throw some numbers on this. See here, come down to this bit here. So we've got a function. There's a certain total amount of change that happens on this function over this interval from 0 to 3. Easy arithmetic, of course. And now I'm going to ask a ridiculous question. Is more of that change happening at x equals 1 or at x equals 2? Which of these points in the domain is more of that change actually happening? And again, super easy question, right? Silly question even. Just look at the picture. Well, it's steeper there, so there's more change happening in the general vicinity of 2 than there is not much change happening over here in the general vicinity of 1, right? Perfectly intuitive. You can see that in the numbers, right? So our change density, the derivative, is, well, you just plug in these numbers. Plug in x equals 1, plug in x equals 2. See where it's bigger. 4 is bigger than 2. So this is where there's more change happening. Between these 2 points, that's the one where there's more change. Yeah? Okay. All right. So I claim, and I think this is pretty believable, I hope, that in the same way that my density, aka my integrand, tells me how much and where of my accumulating quantity is happening in my domain, in this case, it does the same for these other theorems. Right, so let's look at this. This is sort of a picture of, if we were to try to make an analogous argument for Green's theorem. So I'm going to start off with a, let's see here, we have a two-dimensional sort of solid rectangle. The boundary of that 2D rectangle is this 4 sides here of this rectangular curve. That's the boundary. Let's talk about the circulation. How much circulation is there going around this boundary? Okay, well, we can just kind of brute force this. Let's see here. Looking at each piece, how much circulation is happening along here? Well, our vector field is going that way. Our dx's are all this way. They're perpendicular. There is no line integral happening here. Right? Likewise, there's no line integral happening here either. Again, the field and the dx vectors, again, orthogonal. So 0 along those pieces of curve. Now, that said, let's look at this piece of curve right here, this part of the boundary. The field, which I like to think of as a fluid flow, is going that way. My dx's also going that way, same direction. Positive dot product. We're going to get a positive contribution to the vector line integral down there. And now let's look at this top piece over here. Well, the top piece goes like that. Again, keep in mind counterclockwise and all that. The vector field still going that way, but our dx vectors are now going the exact opposite way, which means that the dot product is negative, and that means that the amount of line integral that we get up here is negative. So we have 0 on the left side, 0 on the right side, positive on the bottom, negative on top. How does that add up? Well, it adds up to, wait a minute, we've got a plus and we've got a minus. There's going to be a tug of war between these two terms here. Notice the field lines are longer down here in the bottom. So this is a bigger positive than this is a negative. And that means grand total of the circulation around the boundary is going to be positive. All right? So grand total, again, positive overall circulation. Now, again, reminder, I measure it on the boundary. That's where the formula for it is. It's defined as something you compute on the boundary. But that doesn't mean it's actually happening on the boundary. Of course not. It's happening in the interior. It's an accumulating quantity. It's literally adding up and accumulating over the interior. So in some sense, this circulation that I measure on the boundary is happening in the interior. And we can tell specifically where it's happening even. Because let's look at, let's see here, let me drop a leaf right into the little flow right there. Let's think about what happens to this leaf as the fluid flows along it, and well, that leaf is going to go downstream. Of course it is, right? But will it be rotating as it goes? Well, let's see. It's going to be across the top. It's going to be pushed clockwise, you might say. Across the bottom, it's going to be pushed counterclockwise, you might say, and same amount on both sides. This is not going to be rotating. There's no circulation happening here. That makes sense? Likewise, there is no circulation happening over here. And likewise, there's no circulation happening down here. Down here, now there's a stronger flow along the sort of the top edge there, pushing it stronger clockwise, but it's also stronger down below, pushing it stronger counterclockwise. And again, same amount on both sides. And so no circulation down here either. But you can imagine, and if we were to drop the leaf here instead, well, again, it's being pushed on both sides. It's being pushed clockwise across the top, counterclockwise along the bottom. But check it out. It's being pushed harder across the bottom. The vector field's longer down here. So this leaf in this gray region is going to be twisting. It's going to be turning as it flows downstream. That's the circulation. Now, I measure it on the boundary, right? The grand total circulation, I measure it on the boundary. Yeah, fine. That's where it's happening. And if you compute Green's operator, and again, this is a manufactured vector field that I just kind of made up, but if you were to write down formulas and stuff and actually compute dq dx minus dp dy, at this point, Green's operator is positive. At these points up here and down here, Green's operator is 0. Green's operator will literally tell you where. The circulation that you measure on the boundary is literally happening in the interior. Is that cool? Now, likewise, again, for all of these accumulating quantities, let's look at the other one that we have working for us right now. That's divergence and flux. So again, I can look at this boundary. I can talk about how much flux there is on that boundary. I measure it on the boundary. The formula is defined on the boundary. And so, okay, sure, we'll, keeping in mind that boundaries are oriented outward. Again, standard convention. Arbitrary, but standard convention. Let's kind of talk through it. We look at the various pieces on the bottom. My fluid's going that way. My normal vectors are that way. They're perpendicular. Dot product is 0. There's no flux through this bottom edge. Likewise, there is no flux through that top edge. Okay. What about the left and right? Well, across the right edge, the fluid is going that way. The normal vector through my edge is also that way. Same direction, positive dot product. I get positive flux through that edge. Yeah? Looking at the left edge. Okay, well, on the left edge, the fluid is going that way. The outward-oriented normal, arbitrary but standard outward-oriented normal, is going this way. Those are opposite directions. Dot product is negative. So we're going to get a negative flux across that edge. So again, we find ourselves in a sort of a tug-of-war between two terms. I have a blue negative term and a red positive term, and which one's bigger is going to determine the final answer. Again, let's look at the size of the field vectors. They're pretty small over here, quite a bit larger over here. Same length, right? So which one of these is bigger in magnitude? I think the positive one's bigger. This is a bigger field. So big positive, small negative adds up to positive. Okay, so again, we've done a calculation. We've figured out how much flux, well, qualitatively, how much flux there is happening on this boundary. Again, it's, we measure it on the boundary. That's where we kind of see it, as it were, right? But is that where it's happening? No, of course not. Accumulating quantities don't happen on boundaries. Accumulating quantities happen in interiors. That's what it means to accumulate over some region. Right? Literally, visibly, as in this example, you can see change happening here. So likewise, the flux that we detect on this boundary here, that's just where you're seeing it. Actually, let me zoom out so we can see better. There we go. Sure, we see it on the boundary, but where is it actually happening? And again, let's look at little little pieces in the middle. If I look at a region about like this little green region here, it just kind of at a glance kind of appears there's just as much flux inward into the left side as there is outward from the right side, because the vector field is pretty constant. So I don't think there's any flux happening here. I can literally kind of think through how much is happening in that little piece. No flux happening there, or here, or here, or there, or there, or there, or here, or here, or here. Any of those white background areas, you can just kind of see there's no flux happening there. But if you look here, for example, sure, there's some inward flux. Sure, there's some outward flux. But again, notice the vector field is getting longer as I move to the right. And so, there's inward, there's outward, the inward is negative, the outward is positive. But the positive outward is just bigger than the inward negative. And so positive flux is happening there. And if you compute divergence at this point, again, you've got to write down formula for this vector field. If you write down the formula for the vector field, compute the divergence, evaluate at this point, positive. So again, you see the divergence you see the flux on the boundary. It's actually happening right where the divergence says it is. It's actually happening right there. That makes sense? Here's just a different take, kind of a different choice of words. Same idea. Let's talk about what's going on over here. And I'm just going to make a hand-waving appeal here. But I propose, and y'all can actually check this by hand if you want, let's suppose that the vector field were not what it actually is. Let's suppose that the vector field were just kind of uniformly just like this. If the vector field everywhere were just like what I've got in blue over here, there would be no flux on the boundary. Right? And likewise, if the vector field everywhere uniformly were just like it is over here on the left side, there would be no boundary flux. Right? So that's just kind of another sort of take on the flux that we see on the boundary. It's not coming from here. It's not coming from here. It's coming from in there. Anyway, like I say, different take, different point of view. You can throw some numbers on this. Here we go. This is a circulation and flux analog of this change example that we saw earlier. Right? There's an accumulating quantity called change. We have its associated density called the derivative. Where is the change happening more of? Is it happening more near this point or more near that point? I will plug into the density. The density will tell you literally how much is happening near these points. That's what a density is. Right? And likewise, totally analogously here, given a vector field in a rectangular box. Looking now at these 2 points inside of the rectangular box. Of all of the flux that's happening on this box, is more of the flux happening near this point, or is more happening near this point? Well, look at your flux density and plug in these 2 points. Our flux density is divergence. You can evaluate that divergence at these 2 points. You can look at the results and see which one is bigger. That's the one. So there's more flux happening at 3,3 than there is happening at 2,4, where the divergence is lower. The divergence tells you where the flux is happening. Just like the derivative here, the derivative tells you where the change is happening. And then analogously, and I think we're going to be out of time, but analogously, Green's operator will tell you how much of the circulation you're interested in is happening at these, in the vicinity of these 2 points. Again, just look and see which one is greater. The Green's operator tells you where the circulation is happening. Okay, all right, this is a great stopping point. We will call it a week, and I'll have a great weekend. See you later.